So here we have two parallel currents, and we want to look at how they interact with one another. That let's say we want to know the force on the bottom current. You would then do a curly straight here with the top current, and I hope you are doing that, and the result should be that the magnetic field is going into the page here, and then I would do a cross product of this current with that magnetic field going into the page, that the magnetic field is going to be buoy over the C. Call this current A, this would be current B, and then you would take some length of the wire and cross it with that magnetic field from the other current. If the wires are parallel to one another, then that magnetic field that you get here is completely perpendicular to this length of wire, and so I can dispense with the cross product, and I get this, which is kind of ugly looking. Why are we spending time getting ugly results? But I think it is interesting because it is exactly how current is, the units of current, the ampere, is defined in 1946. That you have two parallel straight conductors of infinite length, and then they're placed 1 meter apart, and they would produce a force, boom, 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 per meter of wire length. So the value we're going to put in for L is a 1 here, and R is going to be 1. And then this gives you the opportunity to say that this mu naught then is defined in terms of this definition of current, that mu naught is equal to 4 pi times 10 to the minus 7. And if you then divide that by 2 pi, you end up with this result, being, if each of these is carrying 1 amp, is 2 times 10 to the minus 7. So here is this alternative way of figuring out what the permeability constant is if you are don't have some reference to turn to. Of course, you'd have to remember that that's the result you're supposed to get. I pointed, that's the permeability of free space, and if there were some other material in here, then this would need to be multiplied by some equivalent of a dielectric constant, a diamagnetic constant perhaps. Remember that when we dealt with capacitance, we had we started off with the permittivity of free space, but then if it were not a vacuum, then we had to introduce this dielectric constant to get what the actual value was for that bit of space that was not free. Just to get you ready for homework, here is an example from the book where they are trying to get the magnetic field strength at point P, and you have these two wires each carrying different currents, and the distance D is 5.3, and if that's a right angle, then you would have to do these legs, you would have to divide that 5.3 by the square root of 2, and that's the value you'd be putting in for R. But you don't want to do it this way. If it's a long wire, then you ought to go with buoy over the sea to get that. And you would just do that for each of the wires, realizing that the magnetic field is going around in a circle. So for this current 1, you get B. Current 2, you get B2, and for current 1, you get B1 going off tangent to the circle at that point P. And just for curiosity, and we'll look at some video of this and talk more about it, this is a rail gun. Here are your rails. Why is that making a circle? You send a current up this rail. Hope nothing's going to start twisting around here, and then it goes across through this conductive fuse, they call this red thing, and then it goes back down the other rail. That this material here is when you start to send current around here, it's going to be such a large current that this thing is going to vaporize. At least that's my understanding. And then you'll have all of these ions. But it will be ions which can move along here with essentially no friction. So it can move very fast, that those ions would be pushed. That it would be this current here, you would, of course, due to this current, you would have a magnetic field which went around the wire like that, coming up through the center, and this back rail would have a magnetic field that would encircle that current and go up through the center. So here at this fuse, you would have a current going there to the left and the magnetic field going up. And if you would take the time to do a cross product, I think you will see that you're going to get a force in this direction that would push the fuse down the rail, and then you would put some projectile in front of it and it would be pushed very fast. And in the book's discussion, they claim that it can produce an acceleration of 5 million Gs. That is, it can cause this thing to reach a speed of 10 kilometers per second in 1 millisecond. Well, the advantage of this for weaponry is that if you're trying to shoot down a missile, normally you send up another missile to get it and either make a great big cloud of stuff to get in the way or come close enough to affect it or chase its heat or something. But you have to take into account the fact that from between the time you fire your missile and when it reaches its target, the missile will be moving. So it becomes a very complex thing, anticipating where it is you should aim your missile at. But if you could get this going this fast, at this speed, you could essentially point this at where the missile is now, and you could get your projectile to it while it is still at that location. So there would be the advantage of this. And you will see footage from Dahlgren up in Northern Virginia, where the Navy has indeed been doing research and building prototypes of these rail guns. I took this claim from the book and I wanted to test it out, as I hope you, if you have the time, also feel like you ought to do. So I decided my projectile would be 10 grams and that it would be 2 centimeters wide. So this distance here would be 2 centimeters. And then I used this, what do you call this? The formula, the definition of field strength formula, at any rate. And I put in the current. This eye is this one here, and the length is 2 centimeters. But the this B is going to come from the same eye, but here in these rails, and Um, so um, I'm going to do buoy over the sea to get what that magnetic field would be. Yeah, there's that distance to the center there is a half. Maybe that's where I messed up. That would be the half of the 2 centimeters. Would be the R value I would use in my buoy over the sea. At any rate, I put in this acceleration and multiplied it by 10 grams to get the force. And out of this, I get that the current that you would have to do would be 3.5 million amps, which seems grossly large to me, makes me dubious. When we look at the pictures from Dahlgren, you will be impressed by the size of the cables and the number of parallel cables they have. So they're evidently trying to find a way to deal with extremely large currents. You would see this bank of capacitors to produce all of that current in a very rapidly, but still, I am skeptical of what the book is claiming.